And then for E, 1, so when you divide 1 by this ridiculous number, what's the remainder that you get? And it's just going to be 1, right? Or written differently, 1 equals 0 times, right? It's a multiple of this ridiculous number plus whatever's left over, which is 1. So 1 is always congruent to 1 in any reasonable modulus.
Any reasonable modulus, is that?
Yeah.
Okay.
Yep. And then for this last one, again, if you don't want to actually multiply those out, you can recognize that when you multiply these, right, this digit here is going to be a 1. And modulo 10 is just saying what's that last digit, so this is going to be congruent to 1. Or you could say modulo 10, this is congruent to 7, this is congruent to 3, so their product is congruent to 7 times 3, which is 21, and 21 is congruent to 1.
I mean, yeah, you can also see that if you take like 3-digit numbers and multiply them out, you'll see that the last digit's the only one that matters.
Right, right. And that's another form of just reducing each number modulo 10, getting the last digit, and then multiplying. All right, question 1, no problems I saw with the union or the intersection. When you take a union and you write a set, get rid of redundant elements, so I didn't take off for that, but we usually just list the individual elements once. Intersection is just the things in common. So the union is 1, 3, 5, 7. The intersection is 3, 5, 7. And then A takeaway B is everything in A that's not in B. And that's just going to be the singleton set containing a 1. And then membership table, not too many problems with that. Some people, their rows kind of slanted up or down, and sometimes things got misaligned, but it was pretty easy to tell if that was what was going on. If there were multiple errors, then I took off more points. But for minor errors, not really a problem. All right, question 4, odd numbers. So by and large, this went really well, which is good. Like I say, my one goal, if I had to name one goal, might be I want you to be able to do proofs, convincing proofs. And most people were able to convince me of this. So an odd number is a number that can be written in the form 2k plus 1. So here's a way to do this. Pick 2 odd numbers, and I'll call them R and S. So we know we can write R as 2 times something plus 1. We can write S as 2 times something plus 1. And so RS equals 4k1k2 plus 2k1 plus 2k2 plus 1. And you factor out your 2. And if we call all of this k3, then R times S is 2 times k3 plus 1, which is the definition of R times S being odd. So that would suffice there. There were 2 main issues that I saw here. The first was working with this. And that will lead you to a valid statement about the square of an odd number. But if you're trying to say something about the product of any 2 odd numbers, you need different k's here, unless the 2 numbers happen to be exactly the same. So that was one issue, and that's a pretty minor oversight. Here's the bigger issue, though, that if you did this, I want to make sure you're clear why you shouldn't. All right, so you start with this. This is what we're trying to show. Okay, so if you write something like, we need to show this, that's fine. If you write this and you expect the reader to believe this is true, you've lost the reader, because we don't know this is true. This is what we're trying to show. So just saying something like show, that puts you back on the straight and narrow. But then I saw things like this. We have no reason to claim that this is true, unless it follows logically from something else that we know is true. And we don't know that this is true. That's what we're trying to show. So how can we say this is a true statement? And what you're really saying is, if this is true, then this is true. Well, if this is true, my name is Nick. I can prove that also. I can show that if 1 equals 2, then 0 equals 0, because I can multiply both sides by 0. But does this prove that 1 equals 2? Absolutely not. This is P implies Q, and Q, therefore P, that's a fallacy. That's the fallacy of affirming the conclusion. So don't write anything down for your proof unless you know that it's true, or that it follows logically from something that you know is true. Okay, that's the number one mistake people make with proofs, here, other courses. And it's subtle. And you can do all the right steps that you would do in order to actually come up with a proof. But if you're saying this equals this and you haven't proven it, your proof is technically invalid. All right, the other thing is you cannot prove this by cases. You can find evidence that it's probably true by multiplying some odd numbers and seeing that they're odd. And it might give you a hint how to generalize. But you could multiply 1 million odd numbers together and still not cover all the possibilities. Now, if you're working modulo 2, we can exhaust all the possibilities and show that every odd number multiplied by another odd number gives you an odd number. But if I'm not letting you do modular arithmetic, which I wasn't in here, you have to do something like that. Who said he's kicking in? Alright, so questions about primes. There are an infinite number of primes. Absolutely. This we know completely, without doubt, is true. And we saw the proof that the Greeks did. So there's an infinite number of primes. There's a simple formula for generating the nth prime. I don't know. I accepted false because we don't know of a simple formula. But you could also say unknown, because maybe there is a simple formula. Yeah. So this one could be unknown. But I also accepted false. If it's true, I want to see that simple formula though, because we can have some fun with it. Infinite number of twin primes, that's unknown. That was an example that we talked about of simple to describe facts about primes that we don't know what their status is. As n gets larger, the number of primes less than or equal to n approaches log of n. That is true. That was that quirky little theorem that I gave you one Friday before we started talking about primes more. Every odd prime can be expressed as a sum of an even and an odd integer. Absolutely. Subtract 2, that's an even number, the number minus 2 is odd, add them together, you get the prime. So that's true. Alright, Betty and her graduation. So this was another proof. And again, in most cases, people had the right idea. And if you got pretty close, you got pretty close to all the points. So a few comments. First of all, when you're doing something like this, make sure it's clear what your propositions are that you're working with. Don't just start saying P arrow Q. Unless you're sure that the reader knows what P and Q are.
On the
Yeah.
as n gets larger,
Mm-hmm.
the number of primes smaller than n approaches to natural log of n. I'm putting 10,000. It's giving me 9.
Mm-hmm.
So is
Natural
there,
log of 10,000?
Yeah. That's,
No.
It's like calculus. And the formula I had was the limit of x approaches to infinity of p of x over natural log of x is going to be equal to 1.
Right, so P of X approaches 1 times log of X.
So if you go to 10,000, the number of primes less than or equal to 10,000 approach.
Right, that's this weird prime number theorem that we've had. But let's see. I don't know how your natural logs on the thing. Yeah, so it doesn't look right for small n's. But for really big n's, approaching infinity,
To be close.
yeah. The reason being that your primes tend to get less and less dense, right, as you have more factors. But it's a limit, right, because you still find twin primes sometimes. But yeah, try it for like a gazillion. I don't know what the easiest way is to experimentally validate that.
Yeah.
Google and see if you can find a plot of this over n. Or I'll do that in between classes and we'll get it tomorrow. So that would be interesting to see. All right, so question 6. State your propositions clearly, right? A lot of people finished early, so you probably had time to do this a little more clearly. So I'm going to say C. The following are propositions. So B is the proposition. Let's say C. Betty takes the course. G will be the proposition Betty graduates. J is the proposition that Betty gets the job. And G is the proposition that Betty works out.
You can't use G twice.
Oh man, I thought it would be
Yeah, I had
slick by
that
not
problem
using
too.
C.
I went with W.
Yeah, W Betty works out at the gym.
You go with E for exercise, perhaps. I did not come up with that.
That would be nice. All right, so if Betty does not take the course, she will not graduate. We're told that these are true statements. So this first statement says,
Not C.
if she does not take the course, she does not graduate. That's a premise. Okay, now we're doing things that are like mathematically rigorous here. If Betty does not graduate, then she does not get the job. That's a premise. If Betty works out at the gym, then she will get the job. That's a premise. So at this point, we can combine these first two statements. If she does not take this course, she will not get the job. And it's a chain rule or something fancy sounding. And then I told you on the board, this fourth statement is an and. Betty does not take this course, and she works out at the gym. So we're given not C and works out. That's a premise. And so you can see the contradiction, right? And everybody was able to articulate what the contradiction was. This says she's going to work out of the gym, which means she's going to get the job. So if she doesn't take the course, she gets the job. That's a chain rule of 3 and 5. And then this and this are contradictory. And to make that rigorous,
That's not J and J, right?
yes.
Yeah.
To make that rigorous, you have to use something that says if A implies B and A, then B. So not C implies J and not C is true. Well, actually you have to break this down and say not C is true and W is true, because that's what an and does, and I didn't expect people to do this level. But if you wanted to be perfectly complete, since not C and W is true, not C is true and W is also true. And since not C implies not J and not C is true, then we can conclude not J. And since W is true and W implies J, then J is true.
Not
Did I-
J and J.
I lost myself.
Yeah, and then you just say not J and J is true. And the
Yeah, so not C is true and not C implies not J, and therefore J is true.
Right.
And since this is true and this is true,
That means we're
then
looking
this
at-
is true, but this is false, so this has to be true, and there's your contradiction.
That's verbatim what I put down, you knocked me down 7 points. I'm confused.
7 points.
how are you
You also
channeling-
wrote not J and W up here, so I think maybe you missed that part down here in the corner.
Yes, so I'll take a look at that right after class, but here's what I saw a lot of people do. This last premise, they did this. I'm going to switch to red, because this is wrong. This last premise, they did this. And then they said, since W implies J, not C implies J. And they said, not C implies not J, not C implies J, contradiction. That is not a contradiction.
You sure it's still inconsistent though, isn't it?
It's not.
Not. Doesn't take the course, she does and does not get the job.
If my name is not Nick, 2 equals 2. If my name is not Nick, 2 does not equal 2. Both of those statements are true.
Because your name has no bearing on
Exactly. The only way that we can use this piece of information is if we know not C is true. And that's what that fourth statement tells us. It tells us not C is true. This by itself tells us nothing about whether C is true or false. And so that tells us nothing about whether J is true or false.
When you get to the not J and J stage, do you have to prove that? Do
No.
you prove that with it? Okay.
No, if you got close, I gave you credit, so I probably missed what you were doing. So show me after class. So if you did this, right, I took off 2 points because you had the essence of it there. If I couldn't follow what you were doing and I didn't find this kind of thing, though, then I took off more. So if you think you did that, let me know. All right, does that make sense?
Can you explain how to do the and statement again? Because I was just substituting it in and it didn't feel. That's what you
You mean this fourth one?
No, yeah, but how to show the implications that anding a not J and a J without just substituting it in.
So the fourth one said Betty takes the course and works out.
It's not.
Does not take the course. So this means this is true and also this is true.
Yeah.
Since this is true and that implies not J, that gives us not J. And since this is true and that implies J, that gives us J. So at that point, it's pretty straightforward to say not J is true and J is true. That's a contradiction. But if you wanted to keep writing, I think there's a fancy sounding name that says if this is true and this is true, then their conjunction is also true. And so that's a true statement. And in fact, we know that this is always false. So we've just proven that false is true. That's getting overly pedantic, but if you want to see it, you could do it like that. All right, so maybe tomorrow or Wednesday I'll talk about topics for the midterm, but it will be everything up through and including what we did last week. So it was 3 main subjects: set theory, conditional logic, and number theory. But we'll break it down into a set of topics in a few days. All right. I want to start talking about induction, mathematical induction. And I have a bit of a quandary with this subject because this is a subject that is both very intuitively obvious once you see it, but also demands a certain amount of rigor. And I usually introduce this from the intuitive side, which convinces people that they understand it, and then they never pick up the rigor. And we need the rigor to do proofs, to use this in a methodical way. So I'm going to come to this from the methodical side, the rigorous side, and hope that the intuition follows from there as we start getting into some actual examples and uses of this. But I'm going to start with sort of the formal mathematical notion, and we'll move down to what this means pretty quickly. So let P of n be some set of propositions. And I'm going to force n to be an integer. That's always going to be the case. And I'm also going to say n is bigger than or equal to 1. And that's not always going to have to be true. We're going to put some bounds on it, but it could be bigger than 0, bigger than or equal to 0, or bigger than or equal to 100. But it's always going to be an integer, okay? That part's important. And P of n is just some set of propositions. So for example, P of n could be the proposition that n squared equals 5 times n. And it's a declarative statement, it has a truth value. It turns out P of 0 is true and P of 5 is true, but P of any other number is false. That's okay. It doesn't have to always be true or false. But it has to be a declarative statement for all values of n. And they shouldn't have done 0 because they just finished saying n is bigger than or equal to 1. So it could be anything. P of n could be the proposition that elephants like falafels. And that's going to have the same value regardless of the value of n because n doesn't appear in the statement. And I'm assuming that there's a truth value to that. I don't know if there is. Okay, so it could be anything. It may have an n, it may have a bunch of things inside. It's just a set of propositions. Okay, so here's what mathematical induction says. Suppose P of 1 is true. Suppose further that P of n, if P of n, then P of n plus 1 for all n bigger than or equal to 1. And this is a proposition, so this if-then statement is also a proposition. So suppose P of 1 is true, and suppose this if statement is true for all n bigger than or equal to 1. Then we can conclude P of n itself is true for all integers n bigger than or equal to 1. That's it. That's the whole statement of mathematical induction. So if P of 1 is true, and if P of n implies P of n plus 1, then P of n is true for all n. Seems simple, right? All right, so what can we do with this? Remember our first class, I talked about adding up ones. And I said if you do 1 plus 1 plus 1 n times, you always seem to end up with n. If you add 1,000 ones, you end up with 1,000. If you add 1,000,000 ones, you end up with 1,000,000. But how do we prove that? We can't add up every possible collection of ones, because there's an infinite number of them. And we don't really have anything in our arithmetic arsenal that says if you add n ones, you're going to get n. But we can do this really easily with mathematical induction. So let P of n be the proposition that adding up n ones equals n. And we're not saying it's true, we're not saying it's false, that's just a proposition. The sum of n ones is equal to n. But we can apply the principle of mathematical induction if we can prove two things. First, is P of 1 true? Is the sum of 1, 1 equal to 1?
Yes.
It's not a trick.
Could you prove that?
But it
Is that
could
all
be.
you have to say?
Yes. Because 1 equals 1. We're assuming that we believe some things. So P of 1 is absolutely true. It's just saying that the sum of 1 is equal to 1. P of 5 is true, because 1 plus 1 plus 1 plus 1 plus 1 equals 5. If I had enough paper, I could prove P of any particular number is true. We only have to prove P of 1 is true. And then we have to prove one other thing. If P of n is true, is P of n plus 1 also true? So, suppose P of n is true. That's our premise or our hypothesis. So 1 plus 1 n times is equal to n. How do we know that that's true? because that's what P of n says. And we're starting by assuming P of n is true. So since P of n is true, this is a true statement. So what do we know about adding n plus 1 ones? If we have n plus 1 ones, that's the same as adding n ones and then adding one more one. And because P of n is true, we know that adding n ones is equal to n. So sum of n plus 1 ones is just n plus 1. And so we've proven that P of n plus 1 is true if P of n is true. So we've only proven two things. We proved P of 1 is true, and we proved if P of n is true, P of n plus 1 is also true. But now we can say, therefore, by the principle of mathematical induction, P of n is true for all n. And so we've proven that the sum of n ones is equal to n for any value n bigger than or equal to 1. So this was a simple thing to show, right? We know if you add up n ones, it's equal to n. But the principle is the same that we're going to use in a lot of examples, in a lot of situations. And it always comes down to these two things. This is called a base step, and this is called the inductive step. So we have to prove the base step and we have to prove the inductive step.
We can say P is equal to 2, P plus 1 is equal to 3. So, and 2 is prime, 3 is prime. So all the numbers are prime.
But you have to prove that if Pn is true, then Pn plus 1 is true. So you have to prove the inductive step. If n is prime, then n plus 1 is also prime.
Dependent
For
on
any n, yes.
Oh.
So you can show it for a particular case, but here we showed this statement for any n, right? If we assume Pn is true for any value of n, then we've shown that P of n plus 1 is also true. So that's a good example of why you need to have this inductive step. We could also, I need a whole lot more whiteboard in this room. Let me do this. Here's a different example. Let P of n be the proposition that n equals n plus 1. Is that a valid proposition?
Valid.
It's a declarative statement that's got a truth value. It's a valid proposition. It's going to turn out to be false in all cases of n. But it, as a proposition, is perfectly fine. Suppose we just rush ahead to the inductive step. Suppose P of n is true, then n equals n plus 1. If we add 1 to each side, n plus 1 equals n plus 1 plus 1. And this is P of n plus 1. So if P of n is true, P of n plus 1 is also true. We've satisfied the inductive step of mathematical induction. But we cannot jump to the conclusion that Pn is true for every number n unless we also satisfy a base case. And there's no base case for which P of n is true. So you've got to have both. That'll come up in some interesting ways. We'll prove that all horses have the same color using mathematical induction. let's see a more real-world case. So first of all, what's going on here intuitively? Why does this work? Why, if we have this and this, can we conclude this? Does this make sense to anybody, logically? What's going on?
You know that if any certain case is true, then it implies the next one, and so as long as the first one's true, that implies the next one, and
Yeah.
so on.
We can always count our way up to any particular n. If you want to know P of 20 is true, since P of 1 is true, and this is true, P of 1 implies P of 2. And since P of 2 is true, P of 3 is true. And given P of 3, we know P of 4. And I just keep pointing back and forth enough times, and eventually I'll get to P of 20 and show that it's got to be true. And if I pick 20 billion, I'd eventually get to 20 billion. And for any integer bigger than or equal to 1, eventually I can prove that it follows from something else that's true. But this is where countability is sneaking in. If we were working with n's that came from an uncountable set, we can't do this anymore. There's no way to guarantee that following this will eventually get us to the number that we're interested in. Because we can't order them.
Which is why we're working in integers.
Which is why we're working in integers. Because we're implicitly using the fact that the integers are ordered. And that if we start from 1 and we count in that order, we'll eventually get to any integer. We can get to every integer in that way. So this only works with countable cases. All right, so let me see if I have some fun examples. I have math examples. They can be fun. So sum of the first n positive integers. And we have a formula for that. N times n plus 1 over 2. Let's prove that. So let's prove that the sum of the first n integers is n times n plus 1 over 2. And we can do it with almost no work. We don't need to know anything about series and summations, we just need some algebra and mathematical induction. So first thing to do, make a proposition. We're trying to prove that this is true for all n bigger than or equal to 1.
Is that over 2?
Yes. It could be a greater than or equal to, I agree. All right, so let's make a proposition. So let P of n be the proposition let P of n be the proposition that the sum of the first n primes equals n times n plus 1 over 2. We're trying to prove that P of n is true for all n. So first, let's do a base case.
You said n primes just then.
Integers.
Yeah.
Sorry. Some of the primes are weird. All right, base case. P of 1 says 1 equals 1 times 2 over 2. Is that true? Yes. So P of 1 is true. Our inductive steps show P of n, if P of n, then P of n plus 1 for all n. We're not showing yet that P of n itself is true. We're saying if P of n is true, can we prove that P of n plus 1 is also true? So assume, so here's our proof. Assume P of n. Well, P of n says 1 plus 2 plus 3 all the way up to n equals n times n plus 1 over 2. So we can say this is true because we're assuming P of n is true. Okay? If we know that this is true, we can do things to both sides and still have a true statement. Only because we're starting off assuming this is true. So, I can add n plus 1 to both sides. Agreed? And now it's just algebra. Let me put those in parentheses to make it clear what's going on. So this is n squared plus n over 2 plus 2 times n plus 1 over 2. So I'm just finding a common denominator. Equals n squared plus n plus 2n plus 1 over 2 equals n squared plus 3n plus 1 over 2 equals n plus 1 n plus 2 over 2. So with a few algebraic manipulations, we've proven that if P of n is true, then the sum of the first n plus 1 integers is n plus 1 times n plus 2 over 2. And that is exactly what Pn plus 1 says. Pn plus 1 would be the proposition that 1 plus 2 plus n plus 1 equals n plus 1 times n plus 2 over 2. Does everybody see that part?
Oh, yeah, I see that.
So we are just changing n with n plus 1 and
Yeah.
plus 1 with n plus 2.
Yeah, and you could use a different variable with it. Right, we could have written P of k equals, and then set k equal to n plus 1. So if we know P of n, we've just proven P of n plus 1 is true. And that's our inductive step. And now we say, therefore, by mathematical induction, P of n is true for all n. Which means that this formula is true for all n. And it feels like a cheat sometimes. We almost didn't really do any work. Right? We never actually did anything that dealt with what happens when you add up consecutive integers. But it's a valid proof. All right, so that can get you started on your homework induction questions. We'll go through a lot of examples tomorrow of using mathematical induction. Probably Wednesday we'll start looking at some misuses of this. And I'll make some comments on what the heck this has to do with programming, because this will come up in data structures quite a bit. And then Thursday we'll prep for the midterm. And then Friday's the midterm. It's the weekend again. All right. I will see you next class.